Let me briefly explain what is template. Templates are internal representation of simple shapes or objects. They are encoded as properties of components and their respective spatial features. For illustrative purpose, templates of simple shape are shown here as boundary with directions. The boundary don't have to be closed. They are the most prominent feature surrounding simple shapes. Boundary pixels are directional. Their direction are color-coded, pointing inward towards the figure. This feature is useful for figure ground separation. This design is supported by the discovery of border ownership cells. Generation of templates is mostly a bottom-up process. This happens during the training phases. Let's use simple shape templates as example. Templates is automatically generated by combining local features following a set of biologically meaningful rules. Single or consecutive adjacent curvatures tend to be grouped together. This is consistent with the finding that in the lower visual cortex, there are neurons selective for convex or concave or conjunction of 2 to 3 adjacent curvature events. Curvature with opposing directions surrounding an enclosed convex region tends to be grouped together. It's okay to have overlapping templates. One curvature may be involved in multiple labeling templates. This will improve cover consistency, leading to an overall improvement in segmentation and recognition. Through repeated trial, only consistent contours are kept, and the noisy edges are removed. Finally, we reach a template containing only the essential contours. The templates are classified through one class classifier, as the system only needs to learn positive features from samples. What about negative samples? They are only necessary if we want to differentiate two very similar objects. The learning process also applies to object templates in the later stage. Finally, neighboring shapes that match object templates are grouped together to form the object. We can understand this process intuitively. If we find the eyes, nose, mouth, and they are in the right place spatially, then we locate and identify a face. Object templates are encoded as a spatial combination of simple shapes. The middle figure shows that when parts are put together in the right spatial relationship, the object is formed. Object templates correspond to neurons responding to complex shapes, such as heads, faces, or even faces of public figures. This stage also consists of bottom-up and top-down process. In the bottom-up process, every part and its neighboring parts form different combinations, and they are matched against the object templates, and the templates with the highest score are activated. In the top-down process, potential object templates are evaluated based on their activation profile, whether their parts are fully matched or only partially matched, or not at all. In addition, the winning object templates at this stage provide feedback to lower level, deciding on what basic shapes should be included, or breaking apart segments that contain both figure and background. As you can see, in our system, location, segmentation, and identification proceed interactively and concurrently, which is consistent with psychophysical studies and physiological evidence. This system is also able to handle complex situations such as occlusion, deformable shapes. Under occlusion condition, the partially matched parts are sufficient to activate the right object template, so the system can still recognize the object despite being partially occluded. Under deformable condition, in current version, deformable parts are handled by generating multiple templates for various configurations of deformable parts. But in future version, this could be handled by including the spatial relationship of deformable parts as part of the definition for the object, thus reducing the need for generating many instances of templates. Our system is designed to have a hierarchical representation of shape information, from basic features to parts, then to objects. Deep learning has also demonstrated the ability to learn hierarchical features for the first few layers. The first layer corresponds to basic features. The second layer corresponds to object parts. The third layer learns to combine parts into more complex features. So what's the difference between the two approaches? First, in deep learning, features are normally difficult to interpret, especially in deep networks, and some basic features are missing. While in our system, all features and templates are explainable. Basic features and the rule for generating templates are designed with biological meanings. Second, in deep learning, parts are arbitrary grouping of neighboring features. It does not distinguish objects' contour from other edges. They are sensitive to local features in the form of local edge relations, but not global object shapes. A recent study shows that with disrupted global shape, the performance of human was reduced to 28%, while the performance of neural networks is unaffected. Conversely, local contour change eliminates accurate neural network classification, but cause no difficulty for human observers. In our system, parts are meaningful entities. Each has a clear definition, such as their global contour, internal textures. They have access to global shape information. Our visual system is designed following the principle of neuroscience. In summary, it has the following distinct advantages. First, less reliance on data. It has built-in mechanism to extract basic features and generate consistent templates or internal representation of objects. It requires only a few typical samples to learn, which is similar to how the brain works. Second, explainable results. The decision process of this demo is straightforward. It's easy to track back its decision process. Third, the system is generalized and scalable. At the current stage, this system is only concerned with shape information. It's okay for simple object identification, but we know that identity of object is defined not only by shape, but also by appearance, its color, and contexture. If we want the system to handle more complex situations, what we have to do is incorporating more basic features and the process to handle those features. While the overall architecture remains the same, it's easy for the system to scale up. With its unique advantages, this system is especially suited for critical applications with limited data, such as self-driving car, medical image analysis, and industrial fault detection. For the next steps, the system could be improved to handle more complex applications by incorporating additional capability such as texture, depth, and motion perception. In a similar fashion, the same approach can also be applied to other modules of the brain function. This is achievable, surprisingly straightforward and efficient if you understand the principle of neuroscience and piece together seemingly unrelated discoveries. When all the necessary modules are completed and integrated together, general intelligence could be achieved. It's not an abstract concept, but a realistic goal. We can work to make this happen step by step right now. Neuroscience has already provided the blueprint. What we have to do is following its guidance and build the system. Thanks for watching. I hope you find this interesting. We are at the dawn of an exciting time where the merge of neuroscience and computer science will usher in a promising AI technology. Due to the time limits of this talk, lots of technical details are not covered. If you want to know more, or for collaboration or business opportunity, please contact us at brainyai@foxmail.com. Thank you.